Hello, everybody, and welcome to another wonderful day of physical chemistry. So today we're going to be going into our last major topic of the semester, spectroscopy. So this lecture is going to try and focus on some of the key overviews of things to look out for as we go ahead and go through the rest of this unit. So one of the first things I want to acknowledge is that how spectroscopy works. So the general move of spectroscopy is essentially one of the big things is it's using light to measure things. So what we're doing is we're going to expose a system to light and either focus in on the absorption or release of a photon by the molecule of interest. So we're going to have an absorption event if I go from a low energy state to a high energy state, and I'm going to have the release or emission of a photon in the subsequent relaxation as I go from a high energy state to a low energy state. So in all these cases, we're just moving in between two energy states, a high and a low, or low and a high, or a high and a low. And the classic form is that we're going to use the amount of energy used in the absorption of the molecule to find the energy difference in between the low energy state that we're in and the next highest or adjacent energy state up. This is classic absorption spectroscopy. We can even find, in some cases, the energy it takes to go 2 or 3 energy levels up. However, one of the other important types of spectroscopy is Raman spectroscopy. So Raman spectroscopy kind of works in a very different fashion. So what we do is we pretty much hit the system with a sledgehammer. We use a very high energy single wavelength of light. So we only have a single wavelength of light coming in. I excite the system to a super high energy state. This can often be done using UV vis or even X-ray light to super excite the system. And then what I do is I watch the system relax back down. So this essentially can be divided into 3 major categories. The first of which is Rayleigh scattering. So that is the case in which I excite the system up with a high energy wavelength, and then it comes right back down into its original state. So it turns out most of you are probably familiar with the idea of Rayleigh scattering because this is how light transmits through the atmosphere. So I'll have, say, blue light hit the atmosphere, gets absorbed by a molecule, then emitted, then absorbed, then emitted, using exclusively this Rayleigh scattering pathway. And the fact that blue light is much more likely to do this than lower energy or higher wavelength light is the exact reason why the sky tends to look blue and takes on different colors. So Rayleigh scattering is the reason for a sunrise. However, there's also several other types of scattering that we're going to be find of extreme interest in Raman spectroscopy. And it's worth noting that these can be found no matter whether we're looking at rotational, vibrational, or even sometimes electronic spectra. So one of the other things that molecules can undergo in Raman spectroscopy is Stokes transitions. So in Stokes scattering, I hit the system with a high wavelength of light, and when it relaxes, it doesn't come all the way back down. It ends up at a slightly higher energy energy state than I came in, meaning that I'm going to have a slightly lower energy of emission. Conversely, we also have anti-Stokes scattering. So this is going to be the idea where when I come back down, I overshoot and I relax down to a lower energy level. And so both of these are very useful because while the Rayleigh peaks aren't going to contain that much information, the Stokes and anti-Stokes can tell us a lot about the energy separation in between these various states. And one of the reasons why this Raman spectroscopy can actually be a lot more useful than simple absorption spectroscopy is because it turns out it's not always possible to perform certain types of spectroscopy on certain types of molecules. Because we have to go ahead and revisit our good old friend symmetry and realize that a lot of our excitations are going to be limited by the fact that a photon is an oscillating electric field, comes in with its own sort of oscillating symmetry. And as a result, in order for an excitation to happen, I have to end up changing the electric field, or in symmetry terms, I have to make sure when I add in this perturbation of a transition dipole moment, which we've used to represent photons before, and I act on my initial state, I have to make sure that this unit has the same exact symmetry as my final state. So another way of saying this is that a photon can only be absorbed if the transition in between my initial and final state is non-zero. And as a result, what we find is that certain types of spectroscopy have what are called gross selection rules. So this essentially is going to be a type of rule that dictates what kinds of spectroscopic transitions are allowed and which ones aren't. And it is worth noting that all types of our spectroscopy are going to have their own set of rules. So we're going to have a different rule for rotational, vibrational, and electronic spectroscopy. So for example, if I've got a pure rotational spectra, so this means I'm only exciting the rotational energy levels, keeping vibrational and translational constant. Turns out the only way I can excite the molecule is if it's polar. Now, one of the reasons why is because as I speed up the if I have a nonpolar molecule, there's no dipole for the photon to act on. So if I've got a nonpolar molecule and I speed it up, I have no new dipole. So I haven't changed the dipole by absorbing an oscillating frequency. The only way I can change an oscillating frequency is by the molecule itself having a dipole. So this means that we can't use rotational spectroscopy to examine nonpolar molecules. Now that gets relaxed with Raman, which is one of the reasons we care a lot about Raman spectroscopy. However, we also, in addition to these gross selection rules, which tells us what molecules can be excited, we also have specific selection rules. So these are going to be the rules that we've talked a lot about already. And so these are the ones that limit the relationship in between the initial and final state. So if I have a specific initial state, I can't excite into any state I want to. Only certain states are accessible. And so, for example, again, looking at rotational spectra, this means that my angular momentum quantum number can only change by 1, which again is a rule that we've already seen before. But now we're going to dive in a little bit more behind its reasoning. So next time, we're going to start with a quick review of our good old friend, rotational spectroscopy. Till then, take care.